Welcome back to RX 2010 Week 4 presentation. We left off talking about allegations and how to deal with the problems when they have ratios instead of percents. The big thing that you need to make sure you remember is to change each ratio to a percent first. So on this particular problem, we are looking at a soaking solution that is a 1:2 soaking solution. We're combining it with distilled water to create 100 mils of a 1:20 solution. Notice we've only got two ratios and we're mixing with distilled water, so that does mean we're doing a dilution. Let's go ahead and change those ratios to percents. 1:2, dividing 1 by 2, you get 0.5. Multiply by 100 to change it to a percent, so it's going to be 50%. And then we're going to also do the same with the 1:20, and that becomes 5%. Now that 5% is the one we are making, so that's what goes in the center. We're using that 50% along with that distilled water. Now we're ready to do our subtraction. 50 minus 5 is going to give me 45. 0 from 5 gives me 5. So I need a total of 50 parts. 5 of those 50 parts are going to be used to make, we're going to use the 50% solution. 45 out of the 50 is the 0% or the distilled water. We're going to take both of those and multiply by 100. And when we do that, we find that we need 10 mils of the 50% and 90 mils of the distilled water. Adding those together will double check for us if we've done this correctly. 10 plus 90 gives me 100. So yes, I do have the correct amount of each, and I have set it up correctly. Okay. Here's our next problem. This one's a little bit different, and I pulled this one out on purpose because it comes out of your textbook. And I have people who run across this and just kind of shut down. They really don't know what to do with it. So let's just go through and pick it apart and kind of talk about it. The prescription calls for alcohol 30%. That's what we're making. And the question says, how many milliliters of a 90% alcohol should you add to 25 mils of a 10% alcohol to make 30%? So we're making 30%. That's what goes in the middle. We're using a 90% and a 10%. So far, everything's just the same. Ready to do our subtraction. 90 minus 30 is going to be 60. 10 from 30 is going to be 20. So we need a total of 80 parts. So 20 out of my 80 are going to be 90%, and 60 out of my 80 are going to be 10%. Good so far. Now remember, on our previous problems, our next step was to multiply by the quantity we want to prepare. We aren't given that information. We don't know how much we want to prepare. The only thing we do know is that we have 25 mils of the 10%. So we know our final amount of the 10%. We don't know our final amount for the total. We only know our final amount for the 10. So we know what this answer is going to be when we multiply by the quantity we want to prepare. And that's all we need to know. We can now use this to solve for this missing piece. Just like if we were solving any other algebra problem, I can find this missing letter. First things first, I hate fractions, and I'm sure a lot of you do too. So we want to change that 60 over 80 into a decimal. Put that into your calculator and you'll find that you get 0.75. So I've rewritten that equation right here. And I've changed the point or the 60 over 80 to 0.75 times n equals 25. Just like before, to get the letter by itself, we have to divide both sides by whatever's with that letter. So I'm going to divide this side by 0.75, and I'm going to divide this side by 0.75. Can't really fit that in there with my tool, so that's why I wrote it in here for you. When you do that, when you take 25 and divide it by 0.75, you're going to find that your quantity is 33.33, and it just keeps repeating. So that's the total quantity that we can make with 25 mils of a 10% solution. So now that we know what that missing piece was, we can go back in and put it into the top equation, this one right here, and find out how many milliliters of 90% we need. Again, I rewrote the equation down here, and I changed the 20 over 80 to a decimal first. 20 over 80 is 0.25. I multiplied by that big long decimal, and my final answer was 8.3 repeating. And I just rounded to the nearest tenth. So it's a little bit different. However, it does produce the same, it does work the same, I should say. We do use the grid in the same manner. All right, so let's move on to our second topic of the evening, and that is parenteral calculations. Parenteral calculations have to do with anything dealing with IVs. There are some formulas in your textbook in Chapter 17. Most of the formulas are some variation of this formula right here. Rate times time equals volume. Whenever we use that formula, we have to make sure that our units of measure are the same. So in other words, if my rate is in milliliters per hour, my time must be hours, my volume must be milliliters. So everything in here has to match, basically. The other thing that you'll be presented with in Chapter 17 is something called dimensional analysis. And dimensional analysis works for all of your problems, regardless of what information is provided, as long as you are careful with your units of measure. Now, I'm going to do one example of dimensional analysis for you. It's a fairly simple problem where most of you wouldn't even think of using dimensional analysis, just so that you kind of get a better idea of how dimensional analysis works. If you like it, great. Use it and make it yours. However, I am also going to work with the formulas for you so that you can see how those work. So let's take a quick peek at dimensional analysis. Here's our problem. If a patient is on a morphine drip in the hospital from Friday morning until Sunday morning, which is a total of 2 days, how many minutes has the patient been receiving this morphine regimen? Now, most of you can do this without setting up this dimensional analysis problem, but I want to use this simpler problem to show you how dimensional analysis works. The first thing you do with dimensional analysis is to identify the question. And our question is, 2 days is how many minutes? So I'm going to write the first part of the question, the 2 days, as a fraction by putting it over 1. So I put 2 days over 1. Now I'm going to use either given information from the problem or, in this case, conversion factors, so that we can get rid of the units of measure. So I have to write them in such a manner that the units will cancel. Because remember, when we multiply fractions, anything on the top on one side and on the bottom on the other side can be canceled. So I know that 1 day is equal to 24 hours. Notice that day is down here and day is up here, so those cancel. Well, right now I just have hours. We don't want hours, we want minutes. So I can take it one step further. I know that there's 60 minutes in 1 hour. I put the hour on the bottom so that those units cancel again. Once you get to the point where you have the units of measure that you're seeking, then you're ready to do the math. 2 times 24 times 60 gives me 2,880 minutes. This is all over 1, so I don't have to do any division. Again, it's a little more complicated to use dimensional analysis. However, some of you might find that it is helpful for you. The rest of our examples are going to all be using the formulas. And like I mentioned, the formula that we are most comfortable with is rate times time equals volume. So that's what we're going to use. And notice I've done the problem both ways. I did dimensional analysis at the top and formula at the bottom. So if you want to see how to do dimensional analysis, it is up here at the top for you. But the formula, rate times time equals volume. Rate is how fast does it flow. So in this problem, the flow rate was 250 milliliters per hour. The time is what we're looking for, and the volume in this case is 2 1-liter bags. Remember, we said we had to have our units of measure the same. So we had milliliters here. We're going to have to change 2 1-liter bags to milliliters also. So 2 liters is the same as 2,000 milliliters. That's where this 2,000 comes from. Now we're ready to divide both sides by that 250. Why 250? Because that's what's with our letter. When we divide both sides by 250, you'll find that T is equal to 8 hours. Okay, let's try another one. Again, I've given you both the dimensional analysis and the formula. With the formula, we have to identify the rate. In this case, the rate is 400 milliliters per hour. We don't know the time, but we do know that we have 2 2-liter bags. 2 2-liter bags is 4 liters. I'll write that over here. 4 liters. 4 liters is 4,000 milliliters. So I'm going to divide both sides by 400 because that's what's with my letter. And T is going to equal 10 hours. Now go back and make sure you answered the question. In this case it says, when will they be completely administered? We started at 7 a.m. 10 hours later is going to be 5 p.m. on the clock. So make sure you take that second step and read and make sure you answered the question that was actually being asked. Okay. This one, we have a patient receiving a 1,500 milliliter infusion over 3 hours. What's the rate infused in milliliters per hour? So rate times time is volume. We don't know the rate, but we know that it is going to take 3 hours and that there's 1,500 milliliters. Divide both sides by whatever's with that letter, in this case 3. 1,500 divided by 3 gives me 500 milliliters per hour. Here's another one. We are looking again for the rate. Rate times time is volume. Make sure you notice that they're asking for the rate in milliliters per hour. So as we said before, we want to make sure that we use the same units of measure. So since it's hours, we have to change 45 minutes to hours. 45 minutes is 45 out of 60 minutes. If you put that in your calculator, you will see that that is 0.75 of an hour. That's where this number came from. We're going to divide both sides by that 0.75 and we get a rate of 400 milliliters per hour.